Good morning, students. Today we will do some problems of Laplace transform and inverse Laplace transform, which are nothing but the applications of differential equation by using Laplace and inverse Laplace transformation. So, Laplace transform method of solving differential equations yields particular solutions without necessary of first finding general solution and elimination of arbitrary constants. Suppose if you simply consider the differential equation 1 is a linear differential equation over 2 with constants a and b. Case 1, suppose in equation 1 we assume a and b are constants and the boundary conditions are y0 and y dash 0 equal to 0. So what will happen then? We know that L of f and t equal to, the formula is for derivative is s to the power n fs s to the power minus n minus 1 f0 in this way, and L of f double dash t equal to s square fs minus s f0 minus f dash 0. So if you take simply L of y square t, f double dash t is nothing but y to the power 2t equal to s square y bar s minus s y0 minus y dash 0. So what you have done here, you will just replace fs by y bar s equal to L of yt, and y square t is second order derivative, and L of y dash t equal to s y bar s minus y0. So how can you solve this differential equation? For that we have to apply Laplace transformation to equation number 1. Then what will I have? A L of y double dash plus b L of y dash plus c L of y, that is L of y equal to L of ft. L of ft is nothing but y bar fs, that is y bar s, and you just use the formula for L of y double dash, that is L of f y square t. What is that? S square y bar s minus s y0 minus y dash 0 plus b L of y dash is what? L of the same formula for L of y dash t. So L of y dash equal to s y bar s minus y0 plus L of y is nothing but y bar s equal to fs. So you just simply plot the values and just use the initial condition y0 and y dash 0 equal to 0 to get the equation a s square y bar s plus b s y bar s plus y bar s equal to fs. Now you just simplify by taking y bar s common to get y bar s equal to fs equal to a square plus b s plus 1. So in this case, from after this step we have to apply the inverse Laplace transform technique. That means we have to use inverse Laplace both sides for this equation to get L inverse of ys equal to L inverse of fs by a square plus b s plus 1. So that is nothing but yt equal to L inverse fs by this. So see, what is our objective? Our objective is to solve the differential equation 1 where y is a function of t. So ultimately, after taking Laplace and inverse Laplace, we will finally got the solution for y equal to t is that. Okay, so by solving this we will get the required answer. Okay, so next case is what? When a and b are not constants, that is differential equation with variable coefficient. So in this way we will just simplify this. The same type of condition we will use to get the equation as t square by t square s square y bar s minus s y0 minus y dash 0 minus dds s of y bar s minus y0 plus y bar s equal to fs. So substituting the boundary conditions in equation 2 and get the values of y bar represented by equation 3. So required solution is obtained by taking inverse Laplace like it is the previous problem for equation number. So this is just the generalization process that the cases we have discussed for case 1 and case 2. These are nothing but the general cases. So for practical problem we have taken the following example, that is you have to solve by the method of transformation of equation y triple dash, that is the third order differential equation, plus 2y double dash minus y dash minus 2y equal to 0, and what are the conditions given to you? y0, that is at at t equal to 0, that is y is equal to t. At t equal to 0, the value of y is 1, the value of y dash is 1, and the value of y double dash is minus 6. So So simply we proceed the equation taking Laplace both sides. Laplace L of 0 is 0. Now we use the formula for derivative in case of Laplace transform for L of y triple dash, L of y double dash and L of y dash to get the equation number 2. Now we have to use this substitute the boundary conditions immediately before solving in equation 2. We will get y bar s, which is nothing but equal to minus 6 by s cube plus twice s square minus s minus 2. So that is y bar equal to, if you resolve the below terms of this fraction to partial fraction, so we will have minus 6 by s minus 1 s plus 1 into s minus 2. Now by resolving into partial fraction, what will you have? Minus 1 by s minus 1 plus 3 by s plus 1 minus 2 by s minus 1. Now from this step we will take the L inverse part. So L inverse of y bar s equals to L inverse of 1 by s minus 1 plus 3 L inverse of 1 by s plus 1 minus 2 L inverse of s plus 2. So in this way we will get yt equal to L inverse of 1 by s minus 1 is nothing but e to the power t, and L inverse of 1 by s plus 1 is e to the power minus t, minus 2 L inverse of 1 by s plus 2 is e to the power minus 2. So this is the solution of y in terms of t with the help of Laplace and inverse Laplace transform. Now similarly, this is the second problem we can easily solve by using the definition to get yt equal to half sin t plus sin t by t. Okay, so what are the hints actually for solving problems in inverse Laplace form? So first hint is, if it is possible to express the denominator as a product of factors, then we can easily use the partial fraction method to find the inverse Laplace form. Sometimes what will happen, it is not possible to express as product of partial fraction. In such case, express the denominator quantity in terms of the form s minus a whole square plus b square or s minus a whole square minus b square. So one more thing is that we have to keep in your mind that the problem in which the denominator is possible to express as a product of partial fraction can be solved in other method also. So some formulas we have already discussed these things by using the problems. So now already told you that if the denominator containing fractions, we can find the value of L inverse by resolving the fraction into partial fractions and to find the L inverse. But there are also some other methods for finding the inverse Laplace transform of those type of functions. So suppose for this problem, if you are going to find L inverse of 1 by s into s plus 2, here what you have observed, the denominator is in the product of factors form, so we can use partial fraction method, or we can use the following method. What is the following method? If L of ft is fs, then L of 0 to t ft dt equal to 1 by s fs. That is the division method actually. So now L inverse of fs equal to ft. Then L inverse of fs by s equal to 0 to t ft dt. So what you have considered here, consider fs equal to 1 by s plus 2. So L inverse of fs equal to L inverse of 1 by s plus 2, that is ft equal to e to the power minus plus 2. So substituting in equation number 1, L inverse of fs by s equal to 0 to t ft dt. So 0 to t, what is your ft here? E to the power minus twice t. So plot it the value, to get the value of 1 minus e to the power minus twice t. So next one is what? L inverse of s by s square plus s square. Similarly, the same method is we can apply, but here the fs is 1 by s square plus s square. So L inverse of fs, L inverse of 1 by s square plus s square, that is nothing but ft is 1 by s sin at. So what is L inverse of dds of fs? It is nothing but minus t ft. So minus t ft equal to, just simplifying this to get the value of ft. So L inverse of s by s square plus s square whole square equal to t by twice as sin t. So the important notes are, if numerator is s and the denominator is something square term, then always TFT model. If numerator is 1 and the denominator is of the something square term, then always it is we have to use T into FT model. If you are asked to find L inverse of log of some term or tan of some term or cot of some term, etc., for any unknown quantity, we don't have any direct formula. In such case, always we have to use the TFT model. Okay, so next we will continue the our unit by using the periodic function of Laplace transform. So what is a periodic function first? A function f is a periodic function of the period t greater than greater than 0 if ft equal to f small t plus capital T equal to f small t plus twice t equal to f of t plus ft. That is, it's an increasing function. For example, sin t and cos t are periodic functions of period twice. So what is the theorem for that? The Laplace transform of piecewise periodic function ft with period t is L of ft equal to 1 by e to the power minus ps 0 to p e to the power minus st ft dt. So proof is not necessary. So if possible, try to find a problem by using this theorem, but it is not given any problem over here also. So after completing this part, in the next class we will discuss lots of problems regarding Laplace, inverse Laplace with period of functions. Now before going to the next class, we want to discuss one more topic today, one or two maybe. So that is nothing but the unit step function, which is simply known as the Heaviside unit function. So what is the unit step function? It is ut minus a, or simply written as ht minus a, which is defined as ht minus a is equal to 0 if t is less than a. That is, for any t less than a, the value of the step function should be 0, or for any t greater than or equal to a, the step function is false, where a is nothing but always a positive. So the graph is given here for ht minus a. Second shifting property or second transformation property. What is that actually? If L of ft is fs and the shifted function gt equal to f of t minus a ut minus a, which can be expressed as 0 if t less than a and f of t minus a if t greater than a, then L of gt equal to L of ft minus a ut minus a, which is nothing but e to the power minus s. So that is again not necessary for this. This is simply the second shifting property over here. Then we will move to the unit impulse function, that is the direct delta function. So what we have to what is the main implication of this function? Suppose for a large force, that is like earthquake, collision of two bodies, acts on a system, produces large effect when applied for a very short interval of time. Now to deal with such type of situations, we introduce a function called unit impulse function, which is a discontinuous function. If a large force acts for a short time, the product of the force and the time is called impulse. To deal with similar type of problems in applied mechanics, and the unit impulse is to be introduced. So what is Laplace transform of ht minus a? It is nothing but e to the power minus as by s. So for Jacobian functions are not required, but I have just written over here. Laplace transform Jacobian function is not included in our syllabus. So simply up to the second shifting property, or up to the Laplace transform unit function, but this unit we will complete this unit with the Laplace transform of units. So now all the theories and few examples regarding Laplace transform and inverse Laplace transform with their applications is done today. So next class we will do some various different types of problems regarding Laplace and inverse and applications of Laplace and inverse Laplace transform. So with this I complete today's video. Thank you.